right? So if q what we had proved was if q is complex, then this, if x is complex, this inequality implies q is equals to 0, but this does not holds for x is equals to r square, right? So now what we are proving is that if H is a question is if H is an Hilbert space and T from H to H is a bounded linear operator, right, whose inverse is bounded, it is given, but to have to show that this inverse exists and this is equals to adjoint operator. Now, since T is a bounded linear operator, T is bijective, and T bijective, that implies T star is bijective, right? And that implies T inverse exists, right? Now, since T in star inverse exists, so what we have is we consider T star T inverse, right, which is equals to T inverse T, which is equals to I, we are given, right? So that would imply if we consider the star adjoint, taking adjoint all over all inequalities, what we have is TT star inverse, TT inverse star, right? So that would be behaving like, now since it behaves like matrix multiplication, so that would be T inverse star and T star. Similarly for second term, that would be T star into T inverse star, which would be I star, and I star is nothing but identity, right? So from this inequality, what we have is T star inverse is equals to T inverse star. That means that the inverse of adjoint operator exists, and that is equals to adjoint of the inverse operator. Okay, any problem in this? Is this clear? Okay. Next is the question that we are given Tn is a sequence of bounded linear operators on a Hilbert space and converges to T. We have to show that the adjoint converges to adjoint of T. Now, so for that we consider Tn minus Tn star, and that would be equals to, now since additive over summation, right? So Tn minus Tn star, right, and norm of T is equals to norm of T star, so यहाँ से that would be equals to norm of Tn minus T, and since Tn converges to T as n tends to infinity, we have Tn star converges to T star. Clear? Any doubt? Sure. Now next we have the self-adjoint unitary and normal operators. Now what is that? A bounded linear operator T from H to H on a Hilbert space is called self-adjoint if T star is equals to P. This is the same as we had matrices, Hermitian matrix or self-adjoint, right? If T star is equals to T. Then if it is symmetric, then if the space was real, we call the matrix as symmetric, right? So here it is self-adjoint or Hermitian if T star is equals to T. Unitary if T is bijective and T star is equals to T inverse, right? So for unitary we need bijectiveness and T star is equals to T inverse, and that would be normal if T star is equals to T star T, right? Same concepts as you are used in matrices. Now next is the definition. How do we define the Hilbert adjoint operator? So this is defined by inner product Txy is equals to inner product x T star y, right? So if T is self-adjoint, then T star would be T and this inequality would hold, right? So inner product of Txy would be equals to inner product of x comma Ty, because for self-adjoint T star would be equals to T. Clear? Now, next is the remark that if T is self-adjoint or unitary, then T would be normal, right? So the main point is O. So if T is self-adjoint, then T star would be equals to T. So if we consider T star, that would be equals to T into T, and that would be equals to T star T, right? So therefore T is normal. Similarly, if T is unitary, then T star is equals to T inverse, and if we consider T star, that would be T into T inverse, that would be identity, right? So similarly, proving for T star T, that implies T is normal, right? Now, the converse is not true. That is, a normal operator need not be self-adjoint or unitary. Now, for example, if we consider the identity operator from H to H, and we consider T is equals to 2 iota into I, then T star by the property of adjoint would be minus 2i into I. because conjugate bahar aayega for the constant, right? And 2 iota ka conjugate is minus 2 iota. So therefore T star would be T star T and T is normal. Similarly, we can find T inverse, right? T inverse is equals to minus 1 by 2 iota, and which is not equals to T star, and therefore T is not unitary, right? So we have the next note. Is this example clear? Right. So for the next note, what we are saying that if there is a basis for Cn, right, and there is a linear operator, then the Hilbert adjoint operator is the complex conjugate transpose of that matrix, right? So as in case of that matrices, जैसे हम देखते थे, जो adjoint operator होता था, that was complex conjugate transpose, right? A star matrix. So that is the same in case of this inner products, that if we are given a certain matrix, a linear operator, then that can be represented by matrix, and its Hilbert adjoint operator would be complex conjugate transpose of that matrix, right? For that, let us consider Cn, right, with the inner product. Inner product on Cn is defined by zeta 1 eta 1 plus this, right? So this can be written as x transpose y, because x and y agar column vectors likhte hain, right? So if we write x and y as column vectors, zeta x को अगर हम लिखते हैं zeta 1 to zeta n, and y को लिखते हैं eta 1 to eta n, right? So for the inner product के लिए अगर इनको multiply करेंगे zeta transpose and y, x transpose and y को, so we would have nothing but the same quantity as inner product, right? So Cn के case में inner product is nothing but this x transpose into y, right? So ordinary matrix multiplication अगर use कर रहे हैं, so we'll get inner product of xy is equals to x transpose y. Next, what we considering is if we define an operator t, right? If we define an operator t, linear operator which is bounded now, right? Because Cn जो है n dimension n finite है, so therefore bounded अपने आप हो जाएगा linear operator, right? So if we consider then if tx को हम define करते हैं ax से, right? So if tx operator goes to ax, then this inner product txy would be nothing but ax transpose y, right? Because inner product of xy को हमने define कैसे किया था? If tx was goes to ax, so txy inner product would be ax transpose y, right? And ax transpose is the normal matrix multiplication, right? Because xy का inner product was x transpose y conjugate. So next is the theorem bounded linear operators. If T is self-adjoint, then this is real, and if H is complex, then this is real. Then this is the operator T is self-adjoint, right? So to prove that if T is self-adjoint, right? So we consider Txy, which is equals to xty, right? And T star can be written as T. So therefore Txy is equals to xty, and that would imply. So now since this holds for all x, so in substituting y is equals to x, we have tx conjugate is equals to x dx by equation 1, and this x comma tx is equals to tx comma x by equation 1, right? So therefore this inner product tx comma x is real, right? Now second, what we had to consider was if h is complex and this inner product is real, then the operator is self-adjoint. So for that, let us consider this first, that H is a complex space and this inner product is real. Any doubt in this? Sure. So the second part, now since Tx is real, so their conjugate it would be equals to this number, right? And inner product of this conjugate is equals to x comma t star x, right? By using of definition of adjoint, and this the conjugate would be equals to nothing but t star x comma x, right? So this holds for every x, right? So taking it in the left hand side, what we would have is inner product tx x minus t star x is equals to 0 for every x belonging to h, since this holds for every x, right? So this would give, now since h was a complex space, so using that lemma we would have is this holds for this qx inner product x is 0 for every x, and h is complex space, so therefore operator is 0, that means t minus t star is 0, and hence t is equals to t star. Clear hai? since H was complex space. Complexity is needed. Okay. Next we have theorem, which is self-adjointness of product. That means if S and T are two bounded self-adjoint linear operators, right? And then if and only if the operators commute, right? So product would be self-adjoint if and only if ST is equals to TS. That right? Just case of matrix multiplication, ST star would be equal to T star S star, and since these are adjoint, T is equals to T star is equals to T. Now we consider the sequence of self-adjoint operators, which says that if Tn is a sequence of bounded self-adjoint operators which converges to T, right? So where that is norm of Tn minus T is 0, then we have to prove that T is also self-adjoint, right? So to prove that, let us consider, since T को हमें self-adjoint दिखाना है, so we'll consider norm of T minus T star, adding and subtracting Tn and Tn star, and then using triangular inequality, right? So we would have this is less than equals to the summations, right? Distributive summations. So now that would be equals to, now Tn minus Tn star 0 है because Tn जो है sequence था of self-adjoint operators, right? Now that would, now Tn minus Tn and norm of T star is equals to Z. So therefore by this, using this, we would have this is equals to norm of ये टू समेशंस बचेंगे एंड दीज टू समेशंस, सो ट्वाइस हो जाएगा नॉर्म ऑफ Tn माइनस टी, एंड Tn जो है T को कन्वर्ज कर रहा था, तो देयरफॉर दैट वुड कन्वर्ज टू 0 एज n टेंड्स टू इंफिनिटी, राइट? सो देयरफॉर यहाँ से क्या आएगा, नॉर्म ऑफ T माइनस T स्टार इज लेस देन इक्वल्स टू 0, बट नॉर्म कैंट बी लेस देन इक्वल्स टू 0 एंड हेंस T इज इक्वल्स टू T star, and that means T is self-adjoint, right? And bounded because limit of bounded operator, right? So next we have a question which says that if S and T are bounded self-adjoint linear operators, right, we have to show that T tilde, which is equals to alpha S plus beta T, is self-adjoint. यहाँ पे S and T जो है दोनों के दोनों self-adjoints हैं, alpha beta real है, right? So T star T tilde का अगर हम star consider करेंगे, T tilde star would be nothing but alpha S plus beta T star, and distributive over summation, so that would be equals to alpha S star plus beta T star, right? And conjugate linear with scalar multiplication, so there could be alpha star and beta star बाहर आएगा, right? And S star is equals to S and T star is equals to T because S and T जो है self adjoint थे, right? So therefore that would be alpha S plus beta T, and that is nothing but T tilde, and hence T tilde is self adjoint. Is it clear?